Hi, I hope everyone's doing well. I'm going to help you with mass spectrometer questions. So on the assignment that was questions 8 and 9, and someone asked me what formula to use. Rather than give you the formula, I want to sort of guide you to develop the formula for yourself. So the question goes like this. This is how we find the mass of a particle the size of a molecule or a subatomic particle like a proton, an electron, or an ion. Now, the particle has to be charged for this to work. In a mass spectrometer, you have a charged mass, so I've called that our ion source here, and it's accelerated through an electric field. So we have an electrical potential, voltage, and that voltage fires the charged particle from here to here, and then it enters a region where there's a magnetic field. Remember, these dots all mean that the magnetic field is coming out of the page towards you. So the charged particle, when it hits the magnetic field, it receives a force. That force causes it to move in a circular motion where it hits a detector. Based on where it lands on the detector, we can determine the radius of its travel, and from there we can work backwards and determine the mass of the particle. So that's how you find the mass of a particle. What I like about this problem is to be able to solve it, you need to review electrical potential, electric fields, magnetic fields, uniform circular motion, kinetic energy, and Newton's second law. So for the first part of it, you've got a charged particle and it's accelerated through a voltage. And when it is, a certain amount of work is done to that particle. Now, how much work is done? You can get work by multiplying the charge by the voltage. I made the V look a little bit funny here because I want you to be able to distinguish it from speed. So when you multiply this charge by this voltage, you get the amount of work that was done to the charged particle. That work is equal to its change in kinetic energy. So a bit of work has been done to the particle, and we now know its change in kinetic energy as it makes its way through here. And remember, your kinetic energy, your change in kinetic energy, assuming that it started at 0, is half mass times the square of your velocity. The particle will then move its way through this magnetic field. And when it does, initially it's going this way. And remember, to find the force on a charged particle that's moving through a magnetic field, we take our left hand, and the force is going this way if the magnetic field goes this way and the current, the moving charge, is going that way. So if my moving charge is going upward and my magnetic field is coming out of the page, then the force on it is going to be this way. So you can apply that left-hand rule yourself, and you'll see that if the charge is moving this way and the magnetic field is coming out of the page, the force that's going to get exerted on that charge is going to be this way. But as that force causes it to change its velocity, the force will also change. It's always perpendicular, which is going to cause that charged particle to move in uniform circular motion this way. When it does, it's going to hit that detector. So the third equation you need is the force due to the magnetic field is the charge times its speed multiplied by the magnetic field. Now, that means cross product, that cross. Its magnitude depends on how perpendicular they are to each other. But in our mass spectrometer, they're set perfectly perpendicular, so you can kind of ignore that. But if you studied vectors and cross product, then you'll know that from that cross product you can determine the magnitude based on how orthogonal those two vectors, velocity and the magnetic field, are. And you can also determine the direction in which that force is going to be applied. But the way I showed you to do that is with the left-hand rule. Remember, force is this way if your magnetic field is this way and you're moving charged particles that way. So you just line them up to determine which way the force goes. And finally, the last equation you're going to need to solve this problem is the centripetal force is mass times acceleration. And the acceleration of an object moving in uniform circular motion is v squared over r. So we're also using Newton's second law here. If you put all four of those equations together, you're going to find you've got several unknowns with several equations, but you keep working your way through it, and from the parameters you've been given in these questions, you can determine the mass of the particle, and that's the point. So again, to recap how this thing works, we have our source of ions, our source of charged particles. They're then released in an electric field. This electric field has a certain potential, and if you multiply the charge by the potential, you get the work that's done to it as the particle is accelerated through the field. That work is equal to its change in kinetic energy. Upon entering this region where there's a magnetic field, the charged particle that's moving this way will receive a force pushing on it that way, causing it to move in uniform circular motion. Remember, you get uniform circular motion when your speed is constant. But if the magnetic field and the charged particle are at right angles from each other, and the force is at a right angle from that, that force that's applied to that charged particle does no work. It changes its velocity, it accelerates it by changing its direction of its velocity, but it doesn't make it go faster or slower. It doesn't actually do any work to it. So you have this constant speed with a constant force towards the center, and then apply Newton's second law to that, and you'll get the acceleration of it. That acceleration will be centripetal, cause it to move in uniform circular motion. The radius, well, that's the diameter I'm showing you here. So if it moves like that, the radius, half of that, would then be determined by the speed that it's going, the force that it receives. You put all of that together, and you'll be able to work out what mass that particle must have had. I know you can do this. Take your time. And let me just quickly represent the four equations you're going to need in case you didn't copy them down. So 1, the change in kinetic energy is equal to work, and the work in an electric field is equal to the charge times the potential. I made that funny looking V for potential. You can then take that change in kinetic energy, and that will be half times mass times velocity squared, assuming it started at zero velocity. The value of the force due to the magnetic field is equal to charge times velocity multiplied by the strength of the magnetic field. And finally, that force, it's going to be the same force. The force due to the magnetic field is your centripetal force. It's the only force acting on that particle. And it's going to cause it to move in uniform circular motion. And the centripetal force is mass times the square of the velocity divided by the radius. You put all of these together and you can easily solve questions, I believe it's 8 and 9 on the assignment. I know you can do this. Of course, you could always just Google mass spectrometer and you'll find one equation that'll isolate mass in terms of potential, radius, charge, and either initial velocity or the voltage that was applied to create that velocity. But don't sell yourself short here. Take the time, work your way through these equations. I know you can do it. Good luck.